Hey everybody, welcome to some more differential equations. Yesterday, or the previous lecture, we looked at what happened when we have a linear differential equation with constant coefficients. And the right-hand side is one of those functions that, quote, doesn't reproduce according to its kind, end quote. And this is definitely one of those things. Now, e to the x does reproduce according to its kind. We compute the derivative of e to the x, we get e to the x. But this 1 over x here messes things up. 1 over x times e to the x, well, let's see. If we compute the derivative of that, we have to use the product rule. And we're going to get 1 over x e to the x minus 1 over x squared e to the x. And if we compute the derivative of that, we just go off into the sunset. Never get this expression back again. So this thing does not reproduce according to its kind. And the only way that we can solve this equation is to use the variation of parameters technique. So we're going to start out by doing what we always do when we have a linear differential equation with constant coefficients. We're going to find the complementary solution. And so we consider the complementary equation, and to get that, we just set the right-hand side equal to 0. So there's our complementary equation. Next, we rewrite the complementary equation using differential operator notation. So second derivative of y, that's d squared y, minus 2 times the first derivative of y, that's dy, plus y itself. So that's the complementary equation written using operator notation. Then we factor out the y. And upon factoring out the y, we discover the identity of the polynomial phi. The coefficient of y, or the cofactor of y, is this polynomial phi evaluated at d. Next, now that we have the identity of the polynomial phi, we form our auxiliary equation, m squared minus 2m plus 1 equals 0. And where did the left-hand side of the equation come from? Well, the left-hand side of the equation is just the polynomial phi evaluated at m. Next, we'll solve the complementary or the auxiliary equation. Yeah, I'll make a note here. This equation is the auxiliary equation. That is, phi evaluated at m equals 0. So let's solve this thing. And we look at it, and this form should look familiar to us. This is nothing more than m minus 1 quantity squared. So guess what? We're going to get a double root. So m1 equals 1, m2 equals 1. Our complementary solution, some constant times e to the m1x plus some other constant times e to the m sub 2x. And m1 and m2 are both 1. We have a repeated root. So we have c1 e to the x. But now if we pull that same trick here, we're going to have c2 e to the x. These are essentially the same solution. One is just a constant multiple of the other. So to get a solution that's independent from this one, what's the trick? What do? Multiply the second one by x, is that right? That's exactly what we do. Now, we have the complementary solution. And since we started out with a differential equation of order 2, we expect to have a complementary solution that has two independent solutions, e to the x and x e to the x. If this had been an order 3 differential equation, that we'd expect to have 3 independent solutions, and so forth. Okay. We have our complementary solution. The variation of parameters technique tells us that we need to take this constant and just turn it into a function of x. Take that constant, turn it into some other function of x, and somehow that will transform the complementary solution into the general solution. So we vary the parameters C1 and C2. We'll call them A of x and B of x, respectively. So this constant C1, we're going to vary that and call it A of x. This constant, we're going to vary that and call it B of x. And our general solution is going to be a of x times e to the x plus b of x e to the x. This is what we propose our general solution to look like. And for some pair of functions, a of x and b of x, this pair of functions, ax and b of x, transforms the complementary solution into the general solution. And as we mentioned in the previous lecture, it makes sense in a way because we know that the general solution has to contain the complementary solution. To get the general solution, essentially what we can do is take the complementary solution and then add to it a particular solution, and that gives us the general solution. So to take the complementary solution and transform it somehow into the general solution makes sense because the general solution contains the complementary solution. And for some pair of functions, a of x and b of x, this transformation actually creates the general solution. Yesterday, we observed that there are actually infinitely many pairs of functions, a of x and b of x. And by the way, they do come in pairs. There are infinitely many pairs of functions, a of x and b of x, that will take the complementary solution and transform it into the general solution. And the fact that there are infinitely many solutions and that we have two independent functions here, a of x and b of x, means that we're allowed to impose two restrictions on this pair of functions. The first restriction that we're going to impose on the pair of functions a of x and b of x is that when we actually plug them in for C1 and C2, we get the general solution. Most pairs of functions ax and bx, if we just plug them in for C1 and C2, won't give us the general solution. So the first restriction that we impose on our pair of functions, a of x and b of x, is that when we plug them in for C1 and C2, we actually do get the general solution. Now, having made that, or having imposed that restriction, we still do have one other restriction to impose on our functions a of x and b of x. Even with this first restriction imposed, there are still infinitely many pairs, a of x and b of x, that will make this a solution. So we have a right to impose another restriction on a of x and b of x. And we'll do that when it becomes advantageous for us. Our next step is going to be to compute y prime and y double prime and plug them into this equation and solve for a of x and b of x. So first, I'm going to have to compute y prime and y double prime. Just so I don't lose my y prime, my y rather, I'll write it up here. Y equals a of x e to the x plus b of x e to the x. Okay. I have a product here. I have to use the product rule. So I have first times derivative of the second, and derivative of e to the x is just e to the x, plus the second, e to the x, times derivative of the first, a prime of x. So here's the derivative of the first term. The second term is also a product. It's a product of three functions. And I'm not sure how most of you learned how to compute the derivative of the product of three functions. So I'll just tell you how I'm going to do it. Take the first prime times the second times the third, or in other words, the first prime times the other two, and then take the second prime times the other two, plus the third prime times the other two. So we get first prime times second times third, plus second prime times, oh my goodness, it's first prime times the other two, plus second prime times the other two. That's much better. Plus third prime times the other two. That's how we do it. Or at least that's how we're going to do it today. So we have first prime times the other two, x e to the x, plus we have the second prime, which is 1, times the other two, b of x e to the x, plus the third prime, that's e to the x, times the other two, b of x, x. And before I do anything, I'm going to simplify this, I think. Well, maybe not. Maybe what I'm going to do first is just impose my remaining restriction for the sake of simplicity. In the example that we did yesterday, we took the two terms that had the derivatives of a and b in them and just said that their sum is equal to 0. That way we get rid of a prime and b prime. And when we compute y double prime, we won't have any a double primes or any b double primes. We'll just have a, b, and a prime and b prime. And 95 to 98% of the time, this is the restriction that we're going to choose. We're going to take the two terms that have a prime and b prime in them and say that their sum equals 0. Okay. This is a prime of x e to the x. And this is b prime of x, x e to the x. And our condition is that we're going to impose the restriction that this equals 0. The sum of these two things equals 0. And by the way, we'll want to remember this because very likely in this solution that we find, or are very likely in finding the general solution, we're going to use this same restriction again. Once we've imposed this restriction, we can keep on using it. Our restriction says that this is true. Well, if it's true, we can keep on using it and using it. Now let's rewrite y prime, and I get ax e to the x, and I get b of x and I have a b of x in both terms here. I have an e of x in both terms here. So let's see. If I factor b of x, e of x, or b of x, e to the x out of this term, I get 1. If I factor b of x, e to the x out of this term, I get x. Okay. And see this here? This isn't y double prime. I apologize for the panic that might have caused you if you noticed that and said, oh, wait a minute, what's he doing? No, this is not y double prime. This is just y prime. And after we impose our remaining restriction, this is what y prime looks like. So now let's compute y double prime. And we have first times derivative of the second plus second times derivative of the first. Now on to this thing. And it's the product of three functions. And remember how I said we do that? We'll do derivative of the first times the other two, plus derivative of the second times the other two, plus derivative of the third times the other two. So derivative of the first, b prime of x, times the other two. Then derivative of the second, derivative of the second, that's just 1. Derivative of the second times the other two, plus derivative of the third, e to the x, times the other two, b of x, 1 plus x. Okay, that's what our second derivative looks like, and it's a mess. Before I simplify it too much, note that we have here a prime of x, e to the x, and here, let's see, we have b prime of x times 1 times e to the x. That's b prime of x times e to the x. And I have b prime of x, x e to the x. And notice something. A prime of x e to the x. A prime of x e to the x. B prime of x, x e to the x. B prime of x, x e to the x. The sum of these two things, or the sum of these two things, is 0. So this term plus this term equals 0. The only term that remains from the sum of these three terms is that term, b prime of x e to the x. These two terms add up to 0. Oh, that's nice. Now, let me simplify again. And yes, this time I really do mean y double prime. And I get a of x e to the x. And over here I get b of x e to the x. What the heck. I'll just write this one down right now. B prime of x e to the x. Okay. So I've taken care of this term. I've taken care of this term. And these two terms have a common factor of b of x e to the x. B of x e to the x. So this is 1 times b of x e to the x. And this is 1 plus x e of x b to the x. So we take 1 plus 1 plus x is 2 plus x. B of x, I'm sorry, let me write it a little bit differently. I'll say b of x e to the x, and we have b of x e to the x times 1, and b of x e to the x times 1 plus x. So 1 and 1 plus x is 2 plus x. That's the remaining factor. Okay. Goodness gracious, great balls of fire. I've got y prime, and y double prime written out. And we're going to remember what our special restriction is. We may use it again. We've used it twice already. We may use it again. Here we have y prime is equal to ax e to the x plus bx 1 plus x e to the x. And y double prime simplified ax e to the x, b prime x e to the x. I'll put that out here somewhere. And I have bx e to the x times 2 plus x. Now what are we going to do? original differential equation, which was y double prime minus 2y prime plus y equals 1 over x e to the x. At least I hope that's what it was. Okay. So I have y double prime a of x e to the x plus b of x e to the x 2 plus x plus b prime of x e to the x. Did I write that down correctly? I think I did. Now I have minus 2y prime. So minus 2y prime. And let's see. That's going to be minus 2 a of x e to the x minus 2 b of x minus 2 b of x e to the x 1 plus x so let's see, minus 2y prime minus 2 ax e to the x minus 2 bx e to the x 1 plus x. Okay. And then we have plus y ax e to the x plus bx x e to the x so I have y double prime minus 2y prime plus y equals ax e to the x is 2ax e to the x minus 2ax e to the x is 0. Oh, thank goodness. So these three wipe each other out. Life should always be that easy. Now, in each of these terms, we have bx e to the x. Here we have 2 bx e to the x minus 2 bx e to the x. So those terms that have bx e to the x but no factor of x, they wipe each other out. 2 bx e to the x, negative 2 bx e to the x. They wipe each other out. Now what do we have here? X bx e to the x minus 2x bx e to the x plus x dx e to the x. Holy moly. I think they add up to 0. Let's see. X bx e to the x minus 2, let me do it differently. X bx e to the x x bx e to the x. That's 2x b to the x minus 2x bx e to the x. They add up to 0 also. Oh my goodness. Oh my goodness, this is wonderful. All we have left is this joker right here. So we get b prime x e to the x and think back to our original equation. Y double prime minus 2y prime plus y prime equals 1 over x e to the x. Well, here we have y double prime minus 2y prime plus y. This is equal to 1 over x e to the x. So in order to find b of x, I just have to solve this equation. This is so easy, even I can do it. Ah, wonderful, wonderful, wonderful. So we have b prime of x e to the x equals 1 over x e to the x. And I'm looking for the identity of b of x. I have b prime of x here. I want b of x. I have a factor of e to the x on each side of the equation. And something that we should remember about e to the x is this. No matter what value of x we plug in to e to the x, we're always going to get a positive number. If you think of the graph of e to the x, the graph looks like this. And it's somewhat asymptotic to the negative x-axis. The graph never touches the x-axis. So the graph of e to the x lies completely above the x-axis, which means e to the x is positive, always. We can plug a ham sandwich in here for x, and we're going to get something positive. Now, my point, and I'm taking the long way around to make this point, but my point is this. E to the x is never 0. No matter what we plug in for x, it's never going to be 0, it's never going to be negative. But the point here is that e to the x is never 0, so we can just divide both sides by e to the x. And we won't be changing anything. So b prime of x equals 1 over x. Can I solve this? Maybe. Let's see, I can integrate both sides. This is b of x. And you may have noticed that I threw away my absolute value bars. And the reason is, at the beginning of the exercise, we were told to assume that x is positive. So x is positive, we don't need the absolute value bars. This is b of x. I'm going to write that up here and put it in a box where I can't lose it. B of x, natural log of x plus some constant. And I'll call it C1, what the heck. Not the same one, not the same C1 we had before, but we're never going to go back to that C1. Well, maybe it will be the same C1. We'll see. Find A of x. And one way that we can do this, probably the easiest way that we can do this, is to use our restriction. And what was that restriction? Let's see. A prime of x, e to the x, plus b prime of x, x e to the x equals 0. That's our restriction. Well, let's see. Again, we can get rid of the e of x's. So we have a prime of x plus b prime of x, x equals 0. Oh, now what do we do? What do we do? What do we do? Well, I knew what b prime was. B prime was 1 over x, wasn't it? So a prime of x plus b prime of x, which is 1 over x, times x equals 0. A prime of x plus 1 equals 0. A prime of x equals -1. Again, this is another one of those things that's so easy, even I can do it. I'll integrate both sides with respect to x. That's it. As scary as this thing looked when we started out, things have turned out remarkably well for us. Ax is natural log of x plus c2. And you know what? I can see that these constants are pretty much going to work out like they did before. Let me just switch the subscripts. I'll call that C1 and this C2. No big deal. I don't have to do this. I'm just being petty. a of x, natural log of x plus c1 times e to the x. Whoa, no. Why didn't one of you raise your hands and stop me? That's not what a of x was. A of x was what? X, just plain old negative x, wasn't it? That's what a was, I hope. So, forget this. A of x, negative x plus c1 e to the x, and b of x, natural log of x plus c2 e to the x. That's our solution. Let's see, b of x, x e to the x. Oh, you people, you're letting me get away with murder. When I make a mistake, why don't you raise your hand and say, Dr. Rossi, did you really mean to do that? And my answer will be, probably not. B of x, x e to the x. Okay, that really is our solution. Now, I don't have to do this, but again, let's just put this in perspective. Look at it from the point of view of particular solution plus complementary solution, okay? Natural log of x, x e to the x. So x e to the x, or negative x e to the x, natural log of x, x e to the x, natural log of x, x e to the x. And then look what we have here. c1 e to the x and c2x e to the x. And we look at that and we say, I know what these are. This is our complementary solution. And everything else is our particular solution. Now, as far as an answer goes, this is fine. But we wanted to keep in mind that even if we use variation of parameters, when we use the technique to take the complementary solution and turn it into the general solution, we do that partly because we know that the general solution is going to contain the complementary solution. And this was our complementary solution. And notice that it is a part of our general solution. yesterday or whenever it was that we had the previous lecture, I said for homework, do page 203, A exercises 1 through 3. And let me just make sure that I'm numbering this correctly. Okay. We'll do the remainder of the A exercises, 4 through 10. And that should give us plenty of practice using variation of parameters. And for linear differential equations with constant coefficients, those are our two tools. Our tool bag has 2 tools in it: undetermined coefficients and variation of parameters. So, this concludes linear differential equations with constant coefficients. Our next topic is going to be what's called Euler Equations, and I'm not saying that correctly. This is a French last name. As Americans, I guess we pronounce it Euler. I never studied French very much, and I'm not a French citizen. I'm sure they would shake their heads in disgust if they heard me pronounce this name. But as Americans, we say Euler. Our next topic is Euler Equations. I'll see you next lecture. And again, take good care of yourselves. Sooner or later, this is all going to be over. And when it is, I look forward to seeing each and every one of you being happy and healthy and sound.